so forth and so forth. Okay, so we're going to start chapter 3, and we're not going to do much in chapter 3. We'll do a few sections. So chapter 3 is dealing with systems of equations. What? I think is it due tomorrow? Night of tomorrow. Oh, yeah. So tomorrow then. So was it to 3, to 4, to 5? They all do tomorrow. Then there's a quiz that's due on Friday. So all the due dates are on my math lab, and I think I fixed them for the proper time zone. No. Yeah. Yeah. And I'll eventually going to be manually typing those numbers into your Canvas grade note. So it will be more standardized for our grading system because it doesn't transfer automatically. So, and if you feel like you were graded on a question unfairly, which happens, let me know and I'll look at it and I'll fix it. I have those types of powers. Does that make sense? A lot of times they ask you, what is the y-intercept? And you say 5, but the answer is 0, 5 as an ordered pair. You should still get some points for that. Yeah, it does it, but sometimes you feel lazy. But yeah, do similar questions. Okay, so systems of equations. So we understand two things right now. If I give you a linear, and for now, systems of linear equations, we're not going to do systems of nonlinear yet. So if I give you a linear equation with one variable, there are three things that can happen. You can get one pretty happy solution, and that happens 95% of the time. You can get no solutions, or you can get infinitely many solutions, meaning all real numbers, right? Remember that. So again, an example of a fun problem, that is an example of a fun problem. We all like that, we can all solve that, blah, blah, blah. I'm not going to go through the details of solving this equation. So here's that one pretty solution. So we like that, right? The next type of equations that we talked about was the linear equations with two variables. So there you automatically get infinitely many solutions. But it's not just, all real numbers. It's a very specific set of ordered pairs that satisfy an equation. So an example would be, again, something friendly like this. Here's an equation with two variables, has infinitely many solutions, and the only way we can possibly solve this equation is to graph it. That was the agreement, that the graph of this equation is, in fact, a solution to that equation. And we all should be able to graph it by now. What is the y-intercept? 1, so we start at 1. And what is the slope? Which means 2 up over 1, right? So whatever this line is, that would be the solution to that equation. Okay, good. So that makes us somewhat happy. But what we're starting now, we're going to start systems of linear equations. And we're just going to focus on the case where there are two variables. So there are two variables and two equations. So first we're going to look at two variables, two equations. Or we usually abbreviate that into 2 by 2 system. Two variables, two equations. We might take a peek at 3 variables, 3 equations, and so forth. So usually have same amount of equations as you have variables. So let me start you off with an example. So here's the system. Y minus x equals 1, and y plus x equals 3. So we usually write it like that. So there are 3 methods of solving this system. And usually when we solve a system of 2 equations, 2 unknowns, it really becomes what we started with, when we just get one pretty solution most of the time. Not always, but sometimes we do. So one of the ways to solve the system is by graphing. Because really what we're looking for ordered pairs that satisfy the top equation and the bottom equation at the same time. Is that okay? Because again, the top equation has infinitely many solutions. The bottom equation has infinitely many solutions. Well, the system will hopefully have one solution. Okay? So if I graph both of those lines, which I should do pretty easily, whatever the point that they intersect will be the point that both solutions share, and that's what I'm looking for. Who's with me on that? You've done that before, kind of? Okay. So graphing. So the first equation, I can graph it really fast. I can just find the x-intercept and the y-intercept. And the way you do that, let me show you. Let me get all fancy here. Can I get all fancy? Yeah, here we go. I'm getting fancy. All right. This is how you find the y-intercept. You set x equal to 0. So what is the y-intercept? Y equals what? 1. So y-intercept is y equals 1. To find the x-intercept, you set y equal to 0. What is x then? No, is it? Negative 1. Very good. So then x equals negative 1. So if I plot these 2 points, 1 and negative 1, so here's the graph, right? At the same time, if I do the other one, what is the y-intercept? And what is the x-intercept? 3. All right, so 3 and 3. Is it? Yeah. So the y-intercept is y equals 3. The x-intercept is x equals 3. So what we have here is 3, 1, 2, 3, 3. So here's the solution. So this point right here, where they intersect, is the solution to the system. Is that okay? Can you, just by looking at this poorly drawn graph, guesstimate what that solution is? What does that point look like, most likely? 1 and 2, right? And it kind of works, right? If you put 2 for y and 1 for x, you do get 1. You put 2 for y and 1 for x, you do get 3. Right? So it does look like, it does look like 1 comma 2 is the solution. Okay? Does that make sense? Now, of course, in order for us to solve these systems graphically, we have to be very precise at graphing. We got to have graphing paper, blah, blah, blah. But that's the idea. You might get a question like this on my math lab. So you just graph both lines, you find the point of the intersection, and that's the solution. Any questions on this? We happy? All right, let's try another one. So here's another example. So here's a system. Y equals negative 3x plus 2, and y equals negative 3x plus 5. Very good. These two lines are parallel. What do you know about parallel lines? So they have the same, so they never touch, right? They never intersect, theoretically. So will this system have a solution then? No. I mean, if I go and if I try to graph them really fast, there will be two parallel lines. One has, intercept at 2, slope is negative 3. Another one has an intercept at 5, slope is negative 3. So do not intersect. So no solution. Okay? We had a fun discussion with another group, the Tuesday-Thursday group, about intersecting parallel lines on the plane, and we did it. We put two parallel lines on the plane, and we intersected them. That was a great success for us. If you behave well, I'll show you how to do that. It's a little mathemagic trick. We're going to intersect parallel lines. But still will not contradict the fact that there are no solutions to this specific system. Happy? Nicholas? All right. And another example. Here's my little system. 3y minus 2x equals 6. And negative 12y plus 8x equals negative 24. So again, I'm going to try to do this one by graphing, and again, the easiest way to graph a line when it's in this form, the standard form or whatever, is to find the x and y intercepts. Putting it into mx plus b form is too much work. So just finding the intercepts, let me make this thing again, make it a little bigger maybe. And here we go. So the x-intercept, you set y equals 0. Can you solve that remaining simple equation? What is x equals? Negative 3. So x equals negative 3. So 1, 2, 3. Bam. And then we'll do the same thing here. That whole thing is covered. What is y? 2, right? It's 3y. Negative is gone. So it's 3y equals 6. So y equals 2. So here's that line. Okay. Is that good? Well, let's try the second one. So if I cover the y and I ask you, what is the x-intercept? 8x equals negative 24. What is x? Negative 3. So negative 3. Right? That's already a solution to that system. That's the point that they share. What if we do this again? What is the y-intercept? Y is 2. So the lines overlap. So how many solutions do we have? Infinitely many, and they're not just all real numbers, it's whatever this line is. Okay? So the solution here is the equation of this line. We can say that the solution, now you probably should, take this line and solve for y to put in mx plus b form. I mean, if we do that, what do we get? If you solve for y equals add 2x divided by 3, so 2/3 x plus 2, right? 2 up 3 over y-intercept is 2. So that's the solution. Okay. Usually the way we express solutions to systems that have infinitely many solutions, we have to create a dummy variable. You can also say like this: solutions would be all ordered pairs where the first x is taken by a dummy variable, whatever you want. Do you have a favorite variable, Nick? n for Nick. So anything goes for n, and then the y will be given by 2/3 n plus 2. So that's acceptable. So these are all ordered pairs that are generated by this little expression. So x is just an independent, the y dependent on x. Does that make sense? So this is what we call a dependent system. It depends on what. Okay. So does the graphical method of solving the systems make sense? Yeah? Did you learn something? What did you learn? What was new? Anyone? Did you learn anything? All right, well, okay. So the other ways of solving the system, and that's how we're mostly going to be doing this. So another technique, and that's called substitution. A substitution method. Who can describe a substitution method to me? Because you all know substitution method, right? You've done that. If I give you a, just make up a system, let's say, for example, 2x minus y equals 4, and then x plus 3y equals -7, just, whatever. And I want you to solve this by substitution. Your first step is to pick a variable. So that means either pick x or y in the first or the second equation. So you have 4 options right now, right? Just pick a variable and solve for it. You really have 4 options. It almost doesn't matter which variable you choose. You're still going to come up with the same answer. Some choices are easier than the others. So if you were to choose for one variable, which one would you choose for? Which one is the easiest to solve for right now? The x in the second one or y in the first one, but you don't want to be solving for y in the second equation, right? So you really want to pick a one that does not have a coefficient. So x in the second, probably the easiest one. So again, doesn't matter. So let's solve for, so in this case, solve for x in equation 2. So then we get x equals -3y minus 7. Right? And then second step would be to substitute for x in the first equation. Right? So we're going to replace that x with whatever it is we got here. So substitute the variable you just solved for into the other equation. So what happens is we get what? 2 times -3y minus 7. And then what? Minus y equals 4. See what I did? Does this make sense? So then we can solve this. This becomes just the one equation, one unknown will like this. So that's -6y minus 14 minus y equals 4. combine like terms, add 14 to both sides. So this is negative 7y equals 18. And finally, y equals negative 18 over 7. So in the third step is to find the other variable. Because at this point we know that x equals negative 3y minus 17 and y equals that. So I can replace x, y in this equation and solve for x. So x equals negative 3y minus 7 and y equals negative 8, negative 18 over 7. So x equals negative 3 times negative 18 over 7 minus 7. I'm getting some really ugly answers, but is that okay? So 3 times 18, what is that? What is 3 times 18? 54. So it's 54 over 7 minus 7. So I need to do the common denominator. So 54 over 7 minus 7 becomes 49 over 7. So the x then equals 5 over 7. Okay? So then the solution is an ordered pair, 5 over 7 and negative 18 over 7. Well, I need to subtract 7, so I have to convert it to a fraction with the denominator. Other questions on this one? So this equation will be very hard to solve graphically. I mean, our answer come out all kinds of weird. So that's almost impossible to do graphically. Let's try another one. Do this one on your own. Two x plus y equals 6, and then 3x plus 4y equals 4, and solve by substitution. So let's do this one really fast. So which variable did you solve for? Yeah, so there's the easiest one. The only one without the coefficient is easy to solve for. So from the first equation, 2x plus y equals 6, we're going to solve for y. So that gives you y equals negative 2x plus 6. Okay, so that's the first step. Second step, we're going to take that expression and substitute for y in the other equation. So that gives us 3x plus 4 times negative 2x plus 6 equals 4. So now that is a pretty simple linear equation. We should be able to solve that. So that's 3x, then distribute 4. So that's negative 8x plus 24 equals 4. Combine like terms, so negative 5x equals negative 20. So therefore, divide both sides by negative 5. X equals 4. Is that okay? Now what? Yeah, so take that, substitute y equals negative 2 times 4 plus 6, so y equals then negative 2. So the solution is 4, negative 2. Is that okay? Let's try this example. 5x plus 4y equals 22. And then negative 3x plus 8y equals 18. Can I ask you to solve this system by substitution? Which variable should we solve for? In which one? Top one. Sure, because in this case, it doesn't really matter. They're all going to be messy, right? Because they all have coefficients. No matter which variable you solve for, will probably produce some sort of a fraction. So it doesn't really matter. If you want to solve for y in the first one, we can do that. It's really flipping a four-sided coin at this point. So if I just solve for y in equation 1, so that is 5x plus 4y equals 22. Subtract 5x from both sides. So 4y equals negative 5x plus 22. And then divide both sides by 4. Y equals negative 5/4 x plus 22 over 4. Right, since 4 divides both terms. Then we can reduce 22 over 4. Y equals negative 5/4 x plus 11 halves. Pretty ugly, but hey, so we have fractions. So then we have to take this expression and substitute for y in the second equation. So we're going to sub for y in equation 2. So what happens then? So that is negative 3x. It's not writing where I wanted to write. It's out of whack again. It was doing so well. And then 8 times negative 5. Yeah, okay, I need to recalibrate this thing again. So let me erase this. So we have negative 3x plus 8 times negative 5/4 plus 11 halves equals 18. Right? We're actually almost lucky that there is an 8 in front of the parentheses, because when you distribute the 8, it kills all the denominators. So that's going to work out better than we thought. It's not completely a messed up example. So negative 3x plus. So the way you multiply 8 by 5/4, how do we do that? We should do it fast. How many times 4 goes into 8? Twice, so then 2 times 5, 10, and there is a minus there, so negative, still not doing, negative 10x. Is that okay? 4 goes into 8 twice. 2 times 5 is 10. And then same thing, 2 goes into 8 4 times. 4 times 11 is plus 44 equals 18. So we can finish solving this. This is a nice little equation. Negative 13x equals, subtract 44 from both sides. What is that going to be? Negative 26? Oh, look how pretty this thing is. And if it's ugly, that's okay. Don't expect all the answers to be pretty. They'll be ugly sometimes. Now, to find y, as the final step, to find y, we go y equals negative 5/4 times 2 plus 11 halves. 5/4 times 2 becomes 5 halves, so negative 5 halves plus 11 halves. Same denominator, so that's lucky. So that is 6 halves. Negative 11 plus, I'm sorry, negative 5 plus 11 is positive 6. So y equals 3. Oh. Solution is 2, 3. Question? Uh-huh. Or you can plug in one of the original. Actually, when you get a number, it really doesn't matter where you substitute it. Okay? It's the only time when you have to be careful with the substitution, when you solve for one variable from one equation, you always have to substitute into the other equation. Because if I take this back into the equation I solved it for, it's going to come out to be 22 equals 22 every time. It's always going to be a true identity because I'm just gun and circles. So yeah, good question. Yeah? Question? That's all you remember? Yeah, go ahead. There is a third way. Yes? Yeah, because, right. Because there is a third way which will really work nicely for this specific equation, where it's no easy variable to solve for, but it's always going to come up with a fraction. There is another way of doing that, and that's called elimination technique. So the third technique, elimination, and I'm not 100% certain that I'm spelling it correctly. Is that close enough? Is that okay? Let me demonstrate elimination technique on a simple system. Can you read me the very first system we solved by graphing? It was pretty straightforward. It was x minus y or something like that. The very first system we did today with graphs. Does anybody have that? This system right there. Y minus x equals 1. Y plus x equals 3. So y minus x equals 1, y plus x equals 3. Okay? So I'm going to demonstrate this technique on this simple equation. Because this equation, if I give you this system, it's really easy to solve by substitution because it's easy to solve for one of the variables. But it is also easy to use to demonstrate this technique. So again, if you notice, our whole process is to turn two equations, two unknowns, into one equation, one unknown. That's what we were accomplishing with substitution. Right at the end, the second step provides us one equation, one unknown. That's what we want. Okay? Are you with me on that? Because we like one equation, one unknown. Now in this case, there is another way to turn this system into one equation, one unknown. Because as you know, when you solve equations, if you add something to one side, you have to add the equal part to the other side. Do you agree with that? Well, since this thing equals 3, they are equal, right? It tells me that y plus x equals 3. Those are equal parts. So if for whatever reason I can take another equation and add y plus x to one side and add 3 to the other side, because I'm still adding equal parts, right? Now, the nice thing happens if I just add these two equations. What is y plus y? 2y. And what is negative x plus x? Nothing. And what's the other side? 4. So in one move, two equations, two unknowns, became one equation, one unknown. And I can solve for y, right? Well, if it doesn't kill a variable, then I'll get two equations. I have one equation with two unknowns, and I don't want that. So I will have to do some kind of tweakage. Well, the way you use elimination is by killing variables. If non-variables kill, if no variable just dies from simple addition, we can tweak it a little bit. But for now, if it's obviously if you add them, x's go away, then just go ahead and add them. Because look, we just found y. To find x, you'd plug it back into any one of those equations, doesn't matter. Or you can kill y magically and solve for x. You can do that too. But anyways, so to find x, just y equals 2, plug it into second equation. 2 plus x equals 3, so x equals 1. All right, so I took y equals 2 and I just plugged it into one of the equations. Doesn't matter. You see, if I plug it in here, it's 2 plus x equals 3, so x equals 1. If I plug 2 in here, right, 2 minus x equals 1, so x has to be 1. So you get the same result in both cases. It doesn't matter which equation you plug in. So the solution is 1, 2. That's what we got by graphing. We kind of guessed that that's the solution from graphing, and it's true. So this is really how elimination works. It's one of the simpler cases where you have a variable that's already, it's ready to be killed. Okay? I can do this system, the one that we kind of struggled with. So here's this example. So if you just simply add these two equations, nothing good will come from it. If you just add the two equations, you will still have an x, you will still have a y, and that's not good. So what you really have to decide first, which variable you want to kill. And the way you kill variable, because again, remember, there are two things you can do to equation. You can add equal parts, or you can multiply by the same number. So you can play with the multiplying both equations by some numbers so that one of the variables has the same coefficient with opposite signs. So if you think about this, one variable has coefficients 5 and 3. The other one has coefficients 4 and 8. So is it easy to make 5 and 3 kind of the same, or 4 and 8? It's basically like finding the common denominator. 4 and 8. Because with 3 and 5, you have to convert both to 15. That's the common denominator. With 4 and 8, you just have to convert them both to 8. And one of them is already 8. Right? So it feels like I should be multiplying the first equation by 2. You agree with that? But I also want to have the opposite sign. I want them to be positive 8 and negative 8. So when I add them, they go away. Right? So I should be multiplying the top equation by negative 2. Is that okay? All right. So let's just do that. I'm just going to multiply the top equation by negative 2. So when I do that, the system becomes negative 10x minus 8y equals negative 44. And then negative 3x plus 8y equals 18. So see what happened? Just changed one of the equations so the coefficients line up with opposite signs. And then you just add them. So negative 10 plus negative 3 is negative 13x. Y's cancel equals negative 26. So x equals 2. Much easier than what we just went through by solving with substitution. When you get all the fractions, it was kind of painful. But here you make them the same and then you kill them. So you have to make one variable to line up. Is that okay? How do we find the y? Yeah. There are actually two ways to find y right now. I can take x equals 2 and plug it into any one of those equations, solve for y, or I can eliminate x and solve for y. That also works. So sometimes if your answer comes out ridiculously ugly, like x equals 2 is easy to plug in, but what if it was like negative 27/41st, something like that. Plugging that in is nasty. So sometimes you're better off killing another variable and starting it from scratch. But in this case, we can just, to solve for y, take x equals 2. Let's plug it into the second equation, whatever. So it's negative 3 times 2 plus 8y equals 18. So it's negative 6 plus 8y equals 18. And the rest is nice and pretty, right? 8y equals 24. So y equals 3. So the solution is 3. Okay? So you can technically use elimination all the time. It works. There are problems that are easy to do with substitution, but they're still going to be easy to do with elimination. There are problems that are very hard to do with substitution, but they're still going to be okay with elimination. So sometimes you'll be asked, like on my math lab, they'll just ask you, hey, solve the system by substitution. And there is no way for my math lab to know whether you actually solved it by substitution, because all you input is the answer. But on the tests, on the little worksheets that I'll give you, they'll be like, solve by substitution, so you have to show the work of solving by substitution. Or solve by elimination, so you have to show the work of solving by elimination. Or it'll just say solve, and then you do whatever you want. Okay? You want to take a break? Yeah? Yeah, go get some water. And so let's, what is it now? Yeah, so it's 9:51. Let's get back at 10.